How we doing?
Good.
Good. Questions by anything before we get into finishing off the least square stuff today? Yes.
Homework questions. I tried attempting one of them, but it's nothing. It's just like, is there a question we can do like senior or TC?
We're gonna do more today.
Okay.
Yeah, that's why I sent all that data in the email today. Yeah. All right. So let's do another one with a linear regression. I want to do a linear regression today. A couple of them. We're also going to talk about ways we can measure how good the model is. So I need to do a little bit of theoretical background there, and then talk about how we can do other types of regression with the linear models. So this first one that we have in here has data from how far a fire was from a fire station, and then how much damage was caused by the fire. So we want to try to predict, in this case, what the damage is versus using how far a house was from the fire station. One thing that you might want to do to see if a linear model even makes sense is create a scatter plot. We can do that in Excel pretty quickly. We just go insert and different types of scatter plots. We can see that with a scatter plot there, that's pretty close to a line, right? So a linear model might work pretty well, looking at the particular data. So I'm going to delete that back out, but that's if you want to see if a linear model works nicely, then I would start with a scatter plot and see what it looks like. All right. So remember last time, the first thing we did was we created that X matrix. If we're trying to make a linear model, our linear model looks like y equals a plus bx. We create that system of equations by plugging in the values for x, plugging out the values for y, and trying to figure out what the a and the b are. The coefficients for your constant are always going to be a 1. In this case, the coefficients for your b's are going to be whatever the x values are, right? So in the first column, I'll just have a bunch of 1s that I'll copy down. And in the second column, we'll just copy the x's over. And get those values. So there's our X matrix. I'll label a capital X up there. That's our X matrix that we talked about last time. XA. It doesn't really matter what the letter is. This is the matrix we're going to start with. So remember from this, we got to create those normal equations. The normal equations, again, we get to that, right? We went through that work last time to get to the normal. This is what we refer to as the normal equations. In order to solve for x, we would want to be able to take the inverse of this matrix. As long as you've got, I'll call it nice data, you need A to have linearly independent columns, and then this will have an inverse. I'm not going to worry too much about that. But I move it to the other side, that's how we get our solution. So basically what we're going to do is just run through, again, how we get that. Oops, these are, yeah, that's right. That's fine. Anyway, so this is how we get our solution. So again, our B value, I really should call this, rather than calling this a B, I'm going to use B for a different letter. This is really what your Y matrix is. So those are your Y values. So it's what that B matrix is. I'm going to call it Y instead. Okay. All right. So going through the commands again, the first thing we need to do is take the transpose of X. There's the transpose. Scooch it over a little bit. So actually, it goes all the way over there, right? So here was our X matrix. Here's our transpose. The next thing we need to do is take that matrix, the A transpose, the X transpose, the A transpose. It doesn't matter what we call it. Later on, I'm going to have an X that I'm using for it. And then multiply it by the X matrix here. AX, again, doesn't matter what letter we call it. So at this point, we should get a 2 by 2 matrix. instead of taking a 2 by whatever times the same whatever cut by 2, right? So I should get a 2 by 2 when I'm done. It also should be symmetric, meaning that when I look at corresponding terms across the diagonal, they should be the same. I should get a symmetric matrix. Yes. That's just doing the transpose of the previous one. Oh, here? Oh, you mean here. That's that mmult command. The next thing I need to do after we multiply this is take the inverse. So remember again, that's the M inverse command of that matrix. And then we take the inverse, multiply it by. So here's our inverse, and we multiply it by the transpose, which is way up here. That was weird. And then at this point, again, we do that times the y. So I need to multiply this one more time. You take this matrix and multiply it by our y, which is over here. So these values. So this is literally the same stuff we did last time, right? So again, take your transpose.
No, I understand the process. I
Okay.
just got like the formulas and stuff. I lost them after the transposing.
Okay, so again, we're just doing it one step at a time. So we took the transpose first. The next one's the multiplication, right? So we want to take, here's our transpose, here's our original matrix, right? So our command is multiply those two together. That's our command, right? I gotta highlight the first matrix, put a comma, highlight the second one. Okay? So that's our command for getting matrix multiplication. After we do that, we take the inverse of the matrix we just found, because that's why we're doing it in steps, instead of trying to type it all in at once. Take the inverse of what we just did. Take that inverse and multiply it by the transpose. And then finally, when we're done with that, we multiply it times the y's. So this is your, I can label it x again. So this first one is x transpose here. I'll just write it as a superscripted t just to save space. This then is the product of your x transpose times your x. Oops. This is your x transpose times the x inverse. This is that thing times your x transpose again. And then finally, you take that whole thing and multiply it by your b. Or your y's, I guess I should say. So again, that's what we're stair-stepping through. We just got to go grab the previous one each time. So again, the coefficients that you get out, this first, the way we've set this up, remember your first column is your constant, the coefficients on that constant piece. That's why they're all ones. So the 10.27793 is the constant, and then your 4.91933 is your slope. In Excel, I remember how to do this quickly. I didn't do it before I came to class. If you put in the scatter plot, and I ask it to That's not what I want to do. Can't do it here. Nope. Forgot how to do it. Like I said, I didn't do it before I came in. I was going to show you how to do it in R. Trend line. Linear. There you go. All I did was I had the chart selected. I said, just did a search for trend line. So I'll put the line in there. And if I format the trend line, it will actually display the equation on the chart, which is exactly the same numbers we got. So again, just to go through that, how I got to that point. When I selected the chart title, I didn't remember where the trend line option was. So I went to the search bar while I was in there and just said trend line and told it to do a linear trend line. So I put it in there. Once I put the linear trend line in there, I just right-clicked on the line and said format the trend line, and then just clicked off display the equation. And it'll show you the equation. Yep. Yeah, and these numbers on here should match what's over there. All right. Let me show you how to do this in R real quick as well, so you can check some things. And then we'll do more with R as we go along. The first thing I'm going to do is I'm going to highlight the data we have, and I'm going to copy it over to a new sheet. And I'm going to put this with a label of X and a label with Y at the top. Okay. So all I did was I opened up a new sheet, copied the data over, gave labels at the top. In this case, I just called them X and Y. The reason why I did that is because I want to be able to refer to these labels when I pull it into R. So let me save this in wherever you're going to put, just like what you did with the data points in your previous, your major assignment. Why can I not find the documents folder? Oh, for heaven's sake, where is the documents folder? There it is. So I'll just call this data to start with. And so I'll save it as a CSV. There's also a read Excel function in R as well. But I'm just going to save it as that particular CSV. And let's get into R here. Just like how you save the points in GeoGebra, just doing the exact same thing. I just want to show you how this works in R as well. All right. I can check to make sure that I'm in that's not where I want to be. I don't want to be in I don't think that's the right folder. I think I just saved it locally. We'll give it a shot. If I do, I'm going to call it data, and I'm going to do read.csv, and I just saved it as data.csv. Oh, I did. Okay, this is the right one. All right, so I'm just pulling the data in just like what you did for GeoGebra, right? So save your CSV file and wherever R is looking for your files, and you can use that read.csv command in there and pull in the data. To create a linear model in R, we use the LM command. I'm going to give it a name because we're going to pull out different pieces in here. I'm going to give it a name with model because I want to be able to pull out different pieces in here. So the command again for finding a linear model is just LM. We want the Y in terms of the X in the data that we just pulled in. So notice I saved my data as data. I read it in as data. Those data have headers. I put an X header and a Y header. I could refer to the Ys by telling it the name of the data. I think R calls it a data frame. The name of the data, put a $, and then the variable that I want to predict. So I want to predict the y from the x, right? Right? Okay. Well, predict the y from the x. So you'll type in whatever you named your data. I named it data. Put a $sign and then the y. And then put a tilde. And then type the exact same thing for the x. So this will create a model, a linear model, for the y values given the x values. That's literally what the command is. Notice when I hit enter, nothing happens because I'm saving it as model. The summary command will spit out a whole bunch of information, and we'll see what all that information is. We're not going to use all of it, but I'll show you what it is. Notice that all sorts of stuff comes in. Okay. Here, for example, is a 5-number summary. You want to do box and whisker plot, for example. These are the coefficients we just came up with in Excel, aren't they? Right. So this gives you the intercept and the slope for your linear model, for your line that we're using for our linear model. This other stuff is from statistics. It's telling you whether or not these things are actually significant. So if you've had some statistics, you can tell that. We're not going to worry about that for our purposes. There is one other number that we're going to talk about that we'll worry about here in a minute. But this just gives you a way to get an R and you can take your answer pretty quickly. So all the work we did in Excel with getting all those multiplications together gives you the same value. A huge surprise that there were things already out there that will give you the same values. That okay? So that's how we do the linear models, both in Excel and in R. So let's see if we can do another one. Let's go back over to the regression data one. Let's just flip over to the next one. This one's a little bit bigger. This would take us a little bit while longer to do this. Oh, I'm just typing what the name of it should be Florida National College. I typed this all in from a textbook. Oh, there's all sorts of typos in there now. I'm looking at it, but that's okay. I don't care about those. Notice that we've got headers in here for college, for retention rate, for graduation rate. This is information about online colleges for retention and then graduation. So the point of this would be to try to predict graduation rate from retention rate. So your graduation rate would be your Y, your retention rate would be your X. All right, so again, I just want to pull this into R. I would like headers in here that are a little bit nicer to work with than having to type this whole thing in R. Okay, so let me just copy this over and I'll give it a different name. So let me copy and paste it in a new file. Oops, and then I want to move this down one spot so I can put it in a header. Get over. Put it, copy it in row 2 so we can put in headers in here. So let me call this retention, and let me call this one graduation, just to give it headers. Again, let's save it as a CSV. And then I'm in my documents here. I'll call it data 2, just to give it a different name. So again, just save it as copy it into a new Excel sheet. Save it as a new CSV file and wherever your R is reading things from. Doesn't matter where, I mean, as long as R can read it, it doesn't matter where you save it or what you call it. Let's read the data back in again. All I did was just arrow up to a previous command, and I'm just going to go in and edit the data too. It'll write over what my previous data was, but I don't really care because I'm not using it for anything else anyway. Okay. All right. So read that file in. If I just type in data, you can see that it's brought in not only the data points in here from 1 to 20, there's 29 data points in here, but it also put in your headers. All right. So I had those headers in there. Remember when I had you do your major assignment, I told you to put that command in there for header equals false, so it doesn't think the first row is a header. Right? Okay. In this case, I want the headers because I'm going to refer to them by their names. Okay. Just like what we did with the data $X, data $Y. Same idea here. But I can actually use those names now that I have for headers if you want them to be a little bit more descriptive. So let's just see, we did a scatter plot first because I didn't do that to start with. I could plot data of retention versus data of graduation. And that'll give you a scatter plot. Right? Again, you might want to do a scatter plot to start with to see if you've got some sort of a general linear relationship or whatever type of function that you're trying to come across. Right? Yeah. Pardon me. So, goodness, apologies. So in this case, it has a general trend of going up and to the right. Right. So looks like possible linear relationship there. So again, give your model a name. Doesn't matter what you call it. I'm just calling it model because I can. Again, for a linear model, the command is LM. My Y's are the graduation rate. Your X's are the retention rate. If I can spell the word retention, that would be helpful. All right. So again, you're trying to get Y as a function of X, and we're doing it approximately, right? It's not going to be exactly that, unless they all fall in a straight line. Again, when you hit enter here, nothing happens. But if I type in summary of model, here would be your intercept, the 25.4229, and your retention here would be the X number here would be your slope. So your model in this case would be Y equals 25.4229 plus 0.28453 X, whatever those happen to be, right? Yeah, lady.
What did you type in to get the summary?
Just literally summary of the model.
Oh.
Yeah. Yeah, the command literally is just summary. If you wanted to create a function and use this for predictions, you can do this in Excel as well. You can do this in R as well. Let's say I give it a function name. Again, I want to be able to plug in an X and get out a Y, right? So I'm just giving it a function name. I'm calling it predict Y. Doesn't matter what it is. Again, give it whatever name you want. If you want to call it F, that's fine. I want to be able to have this as my y-intercept and this as my slope, right? So the way we can do that is just refer to those numbers. Those are actually stored in a list in your model, okay? So the command for that is we stored our model as model, all right? Okay, $sign again. I want the coefficients. Well, your first coefficient is your constant. So I'll just leave that. Okay, so model $sign coefficients 1, and then we want a plus. Same exact syntax, except that I want the second one, and I want to multiply that by the X value. So again, the coefficients is a list of your coefficients. Makes sense, right? First element in the list is your constant. The second element in your list is the slope. Okay. So notice the syntax here looks exactly how we're referring back to the data headers. It's the same idea. We're just using it for the model. If I just type in what the function is, it should spit out what it's supposed to return. All right, so now if I wanted to predict what happens, predict the graduation rate for a retention rate of, say, 72%, it gives us, interestingly, it gives us 45.908, which makes sense based on what it is. I don't know why it's saying intercept at the top, but that's okay. But it's giving us what the prediction is in this case, so you can actually figure out what the values are quickly. So again, this is what R is used for mostly, is doing data analysis and trying to come up with these different things. Questions on how we got any of that? We're going to do more of this as we go along. Any questions on how we got any of that? All right. If we did the next one in Excel, go back over to my data here. We got month and temperature. Again, if we wanted to go through the process, figuring out your normal functions, or excuse me, your normal equations, what would we do first? Okay, yeah, all ones for the A's. And then, okay, so the X's in this case are over here. So just call it all that. So this would be your A or your X matrix, doesn't matter what you call it. All right. We have a column of ones because we're trying to get the constant term, a column of X's because we're trying to get the slope. All right. If we're just doing a straight line model. After we've created this matrix, what do we do with it? Transpose it. So take the transpose of what we just created, right? Transpose of that matrix. Bless you. After we create the transpose, then what do? Multiply it by the original. Good. So that's the mmult command. There's our transpose. There's our original matrix. Right? So highlighting the transpose, highlighting the original. So using that mmult command. And again, at this point, you should be getting a square matrix. The size of the matrix should be the number of rows and number of columns should match the number of parameters you're trying to find. We're trying to find an A and a B, that's why it's a 2 by 2. Okay. If we were trying to find an A, B, and a C, it would be a 3 by 3, and so on up the line. What do we do with that matrix now? Inverse it. So use that matrix inverse command again. After we take the inverse, what do we do with that? Multiply by the transpose. So there's the inverse matrix. There's the transpose matrix. Right? And then finally, the last thing we do is what do we multiply that by? The y values. So take that answer and multiply it by the y values. And get that line. So again, this stair steps through the process, right? Take the transpose, multiply the two matrices together, take the inverse, multiply it by the transpose, multiply by the y. That okay? Now, based on what you know about temperature data, do you expect the line to be a very good fit? No. Let's look at this. Let's do a scatter plot again. Let's insert the scatter plot. There's what the scatter plot looks like, right? If we did the trend line again, do linear, there's our trend line. Doesn't look very good, right? In fact, on here, there's a way to have a measure of how good it is. I'm going to say display the R squared value on the chart. and we'll talk about this r squared here in a second. You can't see it very well, so let's see if I can zoom it. Maybe I can grab the. Why can't I grab the point to make it bigger? Anyway, it says it's about 0.07. Okay. All right. So we're actually going to concentrate on how we can get that particular value, right? That's the idea. Honestly, if you were measuring, if you were trying to get a function to approximate temperature data, what type of function do you think you might use? Yeah, sine or cosine or something like that, right? We would use what's referred to as a sinusoidal function. The problem with that is that it's not linear because one of the parameters that you would have is inside the sine function. Trying to adjust what the period needed to be. Okay. So you wouldn't be able to do the linear models unless you assumed, like for temperature data, that your period was 12. And then you could put that particular thing in there and then get coefficients for sine and cosine. You do it that way. Yeah, maybe.
I don't know. I cannot find the trend line on here. Like I search it and it just doesn't.
Yeah, mine's just like a trend line.
Did you click on that? Trend line? That's super weird.
Yeah, I can't find it either.
Why in the world is it not? That's odd. Is it in the plug? Okay, try that. Where there's a little plus thing. Oh, that's where it was. Thank you. In the little plus thing where it says chart elements, do you get a plus thing when you hover? So if you click on it, oh, that's weird. If you right click, I'm guessing nothing happens that way either. I'll figure that out later. We'll figure it out. I don't know why it's not popping up. We'll figure it out. I don't know why. We'll figure it out. I know there's a way to do it because, well, we can do it. So we'll figure that out later. Okay. All right. Anyway, so let's concentrate on how we can get that R value, but maybe a different type of function fits better. We said sine does, probably would work. So to talk a little bit how we can do something with a sine in it, let me delete this off for the time being. Since it's temperature data, we can assume, let's assume that the period is, pardon me, let's assume the period is 12 for months, okay? If the period is 12, then the coefficient on the inside for your sine function we would need is pi over 6. Remember, you do 2 pi divided by the coefficient on the inside, right? So let's see if we can fit this to y equals a plus b times sine of pi over 6x plus c times cosine of pi over 6x. Okay, and set it up the same way. All right. Okay. So remember again, we used ones here because that's the coefficient on the constants every time, right? But the other coefficients are going to change because what are we going to do to figure out those coefficients on the B and the coefficients on the C? You're going to take the x value and plug it in, right? Here and here. So to get your for your first coefficient, the next coefficients here, I'll do sine of pi over 6 times the x value. So I can't zoom in now. So again, remember to figure out what the coefficients are on the B here, you're going to plug in the answer here or whatever the x value is here and get that number, right? So we just have, and I'm using the pi over 6 to convert the period to 12 rather than 2 pi. Okay. I'll go back in here, but let me zoom in so you can actually see it. So again, just doing sine of pi over 6 times a 2. Okay. Copy that down. What am I going to type in this one? Same exact thing, but cosine. Yeah, cosine of pi over 6 times, it was a2 again, was where the x was, rather than me having to click on it. Same exact function, just changing the sign to the cosine. Okay. Yeah. This now is your X matrix, or your A matrix, whichever way you want to call it. What do we do with that again? Transpose it. So I'll do, I can actually spell the word, every time I try to transpose it, I forget the R. Transpose it. So it's over here. So here was our original matrix. Let me zoom out just a little bit. So everything's on the same screen. After we transpose it, what do we do? Multiply it by the original one, right? So the transpose, what happened? Transpose with the original. Does it make sense that it's 3 by 3? Yeah, because we're trying to find 3 parameters, right? A y-intercept, a coefficient on the sine term, and a coefficient on the cosine term. After we take the inverse, what do we do? Or we got to do the inverse next. I didn't do that one, did I? I got to step ahead of myself. Take the inverse of that matrix. After we take the inverse, what do we do? Multiply by the transpose. So use that mmult command again. That times the transpose, which is up here. And then finally, what do we do? Multiply that by the y's. So here's the matrix we just found. And the y's are way back over here. So this would give you your model. So your model in this case would be 50. Well, the temperature, the y value is 57.58-ish minus 14.323 sine of pi over 6x, and then minus 20.8313 cosine of pi over 6x. So again, as long as it's a linear model, and again, remember the linear part means that you're doing this in terms of, pardon me, you're doing this in terms of the parameters being linear, right? Not the functions themselves, not the sine or the cosine, because those most assuredly are not linear functions, right? Yeah. Okay. All right. But to see how much better this might be, it's a little harder to plot things in Excel. So let's see if I can do this in R real fast. Oh. All right. Well, the caps lock's on. That's a problem. Okay. All right. So let me save this as a CSV file again. I'm just going to call it data because I don't care about overwriting the other one. Oh, fine. I'll call it data 3 then, because apparently I still have the other data book open. Fine. All right. So let's go back over to R. All right, so I read in the data using the read.csv command again. Now, notice that I read it in X and I read it in Y, right? The problem is that I need to take the sine of the x's to get my coefficients, correct? The sine and the cosine. So the way we can do this, actually, is still with our linear model command. I still want to predict the y's, the temperature, right? So I'll write data $sign of y. But if I want to use a different function just by x times something in not Excel, in R, I'm going to use an I to tell it that a different function type of function is coming. On the inside here, I want sine of pi divided by 6 times the x's. Right? This is, when I use the I command again, it's telling R that something besides just something times the variable is coming. Okay? We want to use the function sine of pi over 6x, right? The x's are referred to by the data $sign x. And then on the end here, put in a plus I of cosine of pi over 6 times data x. Again, anytime you want to use something that's different than just constant times x, you use that I command and then tell it what the function is that's coming. Okay. R has no issues with dealing with that. And then do summary of model again to see what everything's going on. And I believe those were the answers that we just came up with in Excel. It really did give us those coefficients again. Okay. So again, you can use Excel to give models that are something other than linear model, other than just functions of x, sorry, not a function of x, just y equals something as a constant times an x. You just have to tell it what the format of the function is by saying, hey, it's a different function besides just x. Notice in this case, if I plot, let's plot the data of x versus the data of y. There's and then I should be able to do, I'm just going to use that. Let me define a function first. You don't have to do this part. I just want to show that the function fits a little bit better. Oh, shoot. Let's return 57.58 minus 14.323 times sine of pi over 6 times x, and then minus 20.8313 times cosine of pi over 6 times x. And then do and then we can plot it in there. And that's a lot better fit than this was what the straight line fit was, right? At least I think that's a lot better fit.
I'm getting an error message in the
Let's see what we got. Oh, you have different names than just X and Y. It read in the headers. So if you use data month for your X and data of that big long thing for your Y.
Okay.
That's why I changed it to X and Y so I didn't type in the long thing. And then again, notice we said something about that R squared value before. The R squared value here is really, really good. Okay. And we'll talk about what we mean by really, really good here in a little bit. But that other R squared we came up with when we just used the line was 0.07. That's really bad. R squared here of 0.9983 is really, really good. So we're going to focus now on how do we calculate that R squared. Okay? All right. So let's talk about that for a little bit. All right. So to do that, notes so I don't mess that up. All right. So we're going to do this from a matrix perspective again, just like what we were doing with everything else with Excel, and show how the computations work. Okay. But the first thing that we want to know about these models and how we're going to give some sort of a measuring stick, if you will, for calculating how good a model is this idea of looking at errors. So again, for our y values, there are some errors that we might want to look at as far as getting our how good our model is. So remember again that our model started out with trying to solve, oops, I'll use X instead of an A here just because that's what my notes has. All right. Our model started out trying to solve this system, right? And try to figure out what the B's were, right? Trying to figure out what this is. Okay. Agreed? That was what we were trying to find out? Okay. All right. So if you let E here be the difference between those two things, this gives you errors, right? If you plug in some how good of a model we have, depends on, I'm using A again instead of a, let me try that again. Erase that. Try that again. This is your error, and we're trying to make this as small as we possibly can, which is what we were talking about with our least square solution and how we came up with those normal equations. But we'd like to get a handle on what error is left from this model, right? We're trying to get a handle on that. What is the least squares idea and the least square error, and how does that correspond to giving us a measure of how good the model is? So one way that we can get at that, remember, is, well, if we just start adding up all the different deviations, we always end up with 0, so we end up squaring things, right? Okay. So when we do our least squares idea, when you do your least squares, if I want the sum of the square error, remember this is going to be, you'll have some error in the first one, an error in the second one, and so on down the line, right? You get that column matrix. If I want the sum of the squared error, I can take the transpose of that error, multiply it by the error, and then I just end up with a 1 by 1 matrix, which gives me the sum of those things. Okay. So when you have E transpose times that E, that'll give you, because I'm doing a 1 by n times an n by 1. So I end up with a 1 by 1, and it just takes E1 times E1 plus E2 times E2 and so on down the line. And then we're going to treat the 1 by 1 matrix like it's a number. Okay? And we're going to do this quite often with some other multiplications. But this is the thing that we're trying to get a handle on. Okay? And we're going to come back to this in a second. All right. So turns out that this part, this sum of squared error, comes up in a different formula when we're looking at just doing deviations from the mean. So for example, if you look at the deviations of each of the y values from the mean and square them, I need to square it because, again, if we do sum of deviations, it will just give me 0 every single time. If you do this, you can rewrite it nicely. So the first thing we're going to do, is add and subtract a y sub I hat All the hat means is it's the predicted value. That's all that means. All right, so what we're trying to say here is that this part over here is your deviations of the data points from the mean. We're trying to get a handle on how we can explain those deviations through predicted values. That's why we're introducing the predicted values here. Okay? So we've got deviations from the mean from the data. I'm going to introduce deviations from the mean using the predicted values. But another piece of that then are the discrepancies between your observed minus predicted values, right? Do we agree with that? Can we see that in there? This part right here are your terms over here, right? Going back up in here, these are observed, these are predicted, right? So each of these pieces right here are the terms in this column matrix. Okay? All right, so getting a handle on this piece here, it pops up in this idea that we're doing of, here's my deviations of each data point from the mean. I've got these error pieces plus the deviations of the predicted from the mean. Now, we're going to show this in a slightly different way, but this actually breaks up how, as perhaps a high school freshman or in junior high, you would have liked this to break up. It looks like the square distributes over the sum. Algebraically, that doesn't work, but those cross terms in the middle, when you do your multiplication, if you FOIL things out, they cancel each other out. We'll see how here in a minute using some linear algebra stuff. Okay. All right. So let me just rewrite that other part here. All right. So each of these pieces have a name. We refer to this one as the total sum of squares, or SST. I know total sum of squares would be TSS, but traditionally it's SST. And then you get arguments for what the next ones are. Some books use it, the letters in one way, and some use it in the other way. Okay, I'm going to use it in this particular way because I think it makes sense pedagogically. This, again, we're trying to get a handle on how far the data points are from the mean, right? If you've done anything with standard deviation before, that kind of pops up in there too, doesn't it? Trying to get an explanation of how far data points are from the mean, right? We're trying to get a handle on this through predictions, okay? So this is your predicted part or the explained part, right? Okay, so I'm going to call that part SSE. Some books call it the other way around, depending on what you're looking at. This is your error sum of squares. This is the part, or if you want to think about it this way, the explained sum of squares. This is the amount of the deviation that's explained by the model. Okay? The other part is this unexplained error, or it's what's left over. What's left over, sometimes you call a residue. Those are called the residuals. Okay? So this is your residual sum of squares, or SSR. Okay. So your total sum of squares, your squares of all your deviations of the data points from the mean, can be broken into two pieces. One is your error sum of squares, or your explained sum of squares here. That's the part that's being explained by the model. This is the error part that's left over. Sum of squares residual, sum of squares explained. Does that make sense? All right. So then the way you can get your R squared value then is that you take your explained sum of squares and divide it by your total sum of squares. Notice that's always going to be a value between 0 and 1. Right? My total sum of squares is made up of 2 positive pieces, so this never can get bigger. So the fraction is always less than or equal to 1. It could be that your model is so bad it doesn't predict squat, and then it could also be 0. But since everything's positive, it can't be less than 0. Okay? So that's why we call this as a percentage, and it gives you a percentage of the error explained by the model, is the interpretation of the r squared. That's why you want a higher r squared, closer to 1 for good models. Does that make sense? All right. So again, this is how the pieces are broken up. I know I didn't go into why this is 0. We're going to do that from a linear algebra perspective here. So let's switch gears a little bit and talk about how we can do this computation through matrices and see that it'll actually agree with what we get when we actually run the programs. All right, so I'm going to define a matrix. I'm going to define a column matrix, a column of ones. That's a Greek letter iota. This is the book I got it out of, using iota. So we'll use an iota. It's just an I with no dot. Okay. All right. When I take this matrix and multiply it by its transpose, notice I'm taking an n by 1 and multiplying it by a 1 by n. What size matrix do I get if I take an n by 1 times a 1 by n? I get n by n, right? Because it's the terms on the things on the outside that get it. And notice the only multiplications you ever do are a 1 times a 1. So it's an n by n matrix. That's just all ones. 1, 1, 1, 1. So that iota times its transpose is just a way to write a matrix of all ones. We're just using symbols because it'll be a little easier for us to do some multiplications later. Okay. All right. The next thing we're going to do is we're going to take this matrix and divide it by 1 over n. So that just means I've got a matrix now with a bunch of 1 over n's in it. All right, so finally now, I'm going to define a matrix that we refer to as n. I'm going to take the identity matrix. Remember, the identity matrix is a matrix that has 1s down the diagonal and 0s everywhere else. So what effect this has is that on the diagonal, I'll get a 1 minus 1 over n, right? Where do we get everywhere else? It'll be negative 1 over n everywhere else, right? Okay. So, all right, what we've done here is create a matrix that has 1 minus 1 over n down the diagonal and negative 1 over n everywhere else. Probably asking at this point, why in the world do we even care? It's okay to ask that. Why in the world do we even care? Okay? Okay. All right. Let's see why. If I take n times y, all right, so it takes a little time to rewrite all these things, but that's okay. All right, so I'm going to write my y as y1, y2, down to yn. Okay? If I didn't have this leading 1 on here, if this minus this 1 weren't here, what would you get when you take the first row times that column? If I take this row and multiply by that column, what would you end up with? Is it a negative 1 over n times the sum of the y's? What's another name for sum of the y's divided by how many y's there are? The mean, right? So that first term in the product is going to be y1 minus the mean, right? Right? The next term will be y2 minus the mean, and so on down, yn minus the mean. Do you agree with that? Okay. Ignore the 1. Negative 1 over n times y1 minus 1 over n times y2 all the way down, right? I can factor a minus 1 over n out. I'm left with the sum of the y's. Sum of the y's over n is the mean. The only thing that gets multiplied by the y1 is that 1. In the next row, the only thing that gets multiplied by the 1 is the y2, and so on down the line. All right. Remember, for total sum of squares, I want to add those up and square it, right? I want to add those up and I want to square each term and add them up to get total sum of squares, right? Remember back up here, I said if I take the transpose times the error, I can get the sum of the squares, right? So if I go back down here and I take the transpose and multiply it by the ny, I get the total sum of squares. So notice I can get total sum of squares by doing this matrix multiplication, but I can actually simplify this a little bit more. Do you remember how to do the product transpose of a product? How does that get rewritten? Some of you have me for linear now. Some of you have had me for linear in the past. Product of a transpose is, or transpose of a product is. Say it again. I didn't hear what you said.
I was just saying, it's just a match.
So if I take the product of any product of any if I take the transpose of any product, how do I do that? We have a formula for doing product or transpose of a product. What would you like it to be? Distribute. Does it just, in fact, just distribute? There is a distribution piece, but it's not just straightforward distribution. What do you have to do with them? You flip the order, exactly. Yeah. So it's a product of the transpose, but you got to flip the order, right? So this will be y. So this way is y transpose n transpose n y. Okay. Transpose of a product is the product of the transposes in the reverse order. Look at your matrix n. Go back up to my n. What do you notice about that matrix? Do you see anything about the matrix relative to the diagonal? It's the same if it's transpose, right? So n transpose is the same thing as n. So right now I've got, oops, I forgot my transpose. I can do the y transpose times n squared times y, but I can actually simplify this just a little bit more. And this is why we wrote n as the way we did. If I want to square this, I would multiply it by itself. And get to that point, right? Just foiling, correct? So I have I transpose squared. Remember your I transpose was that matrix with all ones in it, right? Square matrix with all ones in it. Correct? What happens when you square that? What happens when you square that matrix? What are you going to end up with? If I take this row times that column, what do I get? You know, 1 plus 1 plus 1 plus 1, how many times? N. So this is just going to be an N. What's the next one going to be? N all the way through, right? This is just going to be a matrix full of N's, or I can rewrite it as N times itself. Right? So I just end up with N times itself. So this part right here just ends up being 1 over N I transpose. Those will cancel. So what do we end up with? The 1 minus 1 over N I transpose. Another name for that was what? The N matrix, right? When I square N, I just get N back again. We refer to that as being idempotent. So this computation gives you your total sum of squares. So that Y transpose times the N matrix times the Y gives you the total sum of squares. All right. So now we need to figure out how things break apart, right? I want to try to get my total sum of squares as an explained part and a residual part, right? Okay. All right, so going back up to the way we have this computed, your Y transpose NY again is just that, correct? Right? But remember again that your Y has a predicted part, which was our XB, and a residual part, right? Right, we wrote the error as XB minus Y. So this is just replacing the Y with that. Somewhere I was missing it. What's here? Okay. That's just distributing the N through each piece. Before I do the product here, let's simplify this. If I do the N times the E, again, we defined our N this way, right? is I minus 1 over n I transpose, or iota transpose. Yeah. Oops. Distribute the E. Get that. And now I'm going to do something a little funky in that last term. Oops. I'm going to rewrite it as the transpose of E transpose times iota. Remember what E is? I know, lots of letters, lots of weird things. Remember what E is? Yeah, it's the Y minus the Y hat, or the Y minus the Y hats, right? Or, no, sorry, not the Y minus the Y hats, the Y minus the Y bars, right? Yeah. So your E transpose is going to be this row matrix of Y1 minus Y bar, Y2 minus Y bar, Yn minus Y bar. What was iota again? All ones down a column, right? They agree? What do you get when you take E transpose times iota? What are you going to end up with? So you take that times 1, that times 1, all the way down to that times 1. So you just get those terms. What do you do with all of them? Add them up, right? What am I adding up? I'm adding up deviations of data points from the mean. What do you always get when you add up deviations from the data points from the mean? 0, right? Oops. So if this is 0, this whole term is 0, isn't it? And so we just end up with E. All right. So going back over here, I can rewrite this as NXB plus E transpose NXB plus E here. Okay. Now, one last thing before we stop. I'm going to make your homework due on next Tuesday just because we didn't get it right. Today's Tuesday, correct? Forget what day it is. I'll make it due next Tuesday since we didn't get as far as I'd hoped today. Okay. The good news is when we put this over in Excel, it won't be that bad. We'll just have to do the same kind of stuff. Okay. Yes. Yeah, just email me the files that you need. But let me finish this off to a certain spot, okay? So I would remember the transpose of a sum is the sum of the transposes, right? And then the product of the transposes is the transpose of the product is the product of the transposes in reverse order, correct? Okay. So here I would get B transpose, X transpose, N transpose, we already said N transpose was N, right? Plus E transpose times NXB E transpose. Now distribute. This times this will give me B transpose, X transpose, N times N, but we said N squared was also N, right? Get XB here, right? In the middle, we'll get B transpose, X transpose, N times E, but we just said that N times E is E, right? Here we'll get E transpose times N, but that's the transpose of NE, right? So this is just going to be E transpose X B, and then plus E transpose E on the end. Okay. Let's take a second and see where we are. Okay. And then we'll finish this up next time. We're almost done, actually. We'll finish this up next time and then practice with some Excel stuff, okay? The left-hand side again was what? This is SST, correct? This is SSR, right? This part is SSR, correct? So what's left here has to be your SSE. That has to be explained part, right? You agree? What's left has to be the SSE. But what's going to turn out is that these two terms right here are going to end up being 0. So this is your SSR. This is going to be your SSE. Okay? So when we get to your R squared, you can compute it by doing this formula. So that's how we'll calculate R squared using Excel. So next time we'll show why that's 0, and then we'll do a bunch of examples in Excel. Sound like a plan? All right, have a good one. We'll see you on Thursday, if not before. But that's going to be how we get to SSE over SSR. The sum of squares explained over that value.
Do you own a TI calculator?
Of course. I'm also pointing you to my YouTube page where there's a whole bunch of videos about doing example problems, exam FM problems. Yeah. I would absolutely let you borrow that. Makes life a lot easier on that exam.